Okay, we're going to walk through the answers to the gas density problems. You already have the actual answers, but let's do the problems together. So this is number 1. What is the molar mass of a sample of gas that has a density of 2.85 grams per liter at 72.1 kilopascals of pressure and 29.0 degrees Celsius? So first, I'm going to rearrange the ideal gas law again for you. So PV equals nRT is the ideal gas law. And if you remember, this N is what's going to represent our quantities, and our quantity is going to be, N is represented by moles, but the quantity we're going to need is grams, because as soon as I see this grams per liter, I know that's a density. So let's replace, if remember, N is equal to the number of moles, and our molar mass is equal to grams per mole. So moles is equal to grams over molar mass. So let's replace N with mass, or grams over molar mass. So PV is equal to mass over molar mass times RT. Let's clarify that in case we're looking for formulas where we're replacing mass. So if you remember, density is grams over volume. So let's make it so we have grams RT on the top, and then molar mass and volume on the bottom. So this can be replaced with density. So molar mass, I'm just rearranging the equation now, is dRT over P. That's the derivation of our molar mass kitty formula, which is a good molar mass kitty puts dirt on top of P. That being said, let's read through the problem. It says, what is the molar mass? So that's what we're solving for. Of a sample of gas that has a density of 2.85 grams per liter at a pressure of 72.1 kilopascals. Remember, in order to use the ideal gas law, my pressure has to be in atmospheres. Standard pressure is 1 atmosphere, which is equal to 101.3 kilopascals, which is 760 millimeters of mercury, which is the same as torr. So I can change kilopascals to any other units I want. In this case, it's atmospheres. So 72.1 kilopascals is actually equal to 0.7117 atmospheres. I'm not worrying about sig figs yet. And then the temperature is 29.0 degrees Celsius, which, in order to change the temperature to degrees Celsius, or from degrees Celsius to K, all I have to do is add 29 plus 273. and that's 302 K. Molar mass is equal to density times ideal gas law constant 0.08206 liters atmospheres per moles K. Temperature 302 K. On the bottom, we put the pressure, which is 0.7117 atmospheres. If all has gone correctly, the units I don't want will cancel out. How they cancel out is by having one on the top and one on the bottom. When you have a same unit on the top as you do on the bottom, they will cancel out. And we are left with units of grams on the top and moles on the bottom. Grams per mole is an adequate unit for molar mass. So I multiply across the top 2.85 times 0.08206 times 302, and then I divide it by the bottom, which is 0.7117, and I get an answer of 99.2399 grams. That's grams per mole. So that's the molar mass of my gas, 99.23 grams per mole. You might also be given a list of known molar masses for gases. For example, oxygen is O2. That's 2 times oxygen, which is 16 or 32. You know this gas is not oxygen because it doesn't have the right molar mass. So you can identify the identity of a gas or determine what gas it is based on its molar mass. Okay, let's do number 2 together now. It says how many grams of gas are present in a sample that has a molar mass of 44 grams per mole, occupies a 1.8 liter container at 108 kilopascals and 26.7 degrees Celsius. So let's write that all down. Grams is a mass, so what we're solving for is the mass in grams. It's giving us a molar mass of 44 grams per mole, and it's giving us a volume of 1.8 liters, a pressure of 108 kilopascals, and a temperature of 26.7 degrees Celsius. Let's remember that we have to change kilopascals to atmospheres, remembering that there's 101.3 kilopascals in one atmosphere. So 108 kilopascals divided by 101.3 kilopascals in one atmosphere gives us 1.066 atmospheres. 26.7 degrees Celsius, add 273, and you get 299.7 K. Let's remember our molar mass kitty puts dirt over the P. Now, you can recognize that density is mass over volume. So you can either solve for density and split that apart later, or you can change density. Instead of having density, we'll have mass over volume. And then if we solve for mass, we can say, let's rearrange the equation to leave mass by itself on this side. So we can move volume over by multiplying each side by volume. We'll move pressure over by multiplying each side by pressure. Move R and T over by dividing each side by R and T, and that's going to allow us to solve for our mass in grams. So now we can plug in 44 grams per mole, 1.8 liters, 1.066 atmospheres over 0.08206 times 299.7 K. So let's see, we've got moles in the bottom, atmospheres cancels, liters cancels, Ks cancel, and we're left with an answer in grams. And we're going to answer to 2 sig figs. I think the answer key gives it to you in 1 sig fig. We won't stress that. Some people don't worry about sig figs very often like we do. So I'm going to multiply across the top and divide by the bottom. And that's going to give me an answer to 3 sig figs of 3.46 grams. Okay, now that we've derived the equations, we're going to do the next ones a little bit more quickly. Number 3 states, what is the molar mass? So molar mass is what we're solving for of a gas if 142 grams of it occupies a volume of 45.1 liters at 28.4 degrees Celsius. I'm going to change this to Kelvin right away by adding 273. And a pressure of 94.6 kilopascals. Remember, to change kilopascals to atmospheres, we need to have kilopascals cancel, and we want to change it to atmospheres. The conversion factor is 1 atmosphere is equal to 101.3 kilopascals. You can turn this equivalency statement into a conversion factor by having it stay with its numbers. So 1 always goes with atmospheres, and 101.3 goes with kilopascals. And that gives us a pressure of 0.93386 atmospheres. I won't worry about sig figs right now. So molar mass kitty is equal to dRT over P, or remembering that density is mass over volume times RT over P, which is 142 45.1 liters times 0.08206. I always use my units so I can check whether I'm making a mistake or not when my units don't cancel. And T is 301.4. And P is 0.93386 atmospheres. Let's check our units cancels. Liters in the top, liters in the bottom. K's on the bottom and the top, atmospheres on the bottom and the top, and we have units of grams per mole, which is the good unit for molar mass, and that will give me the correct answer. Let's go right on to number 4. I'm going to be solving for density. STP tells us that our temperature is 273 K and our pressure is 1 atmosphere. And molar mass is 39.9 grams per mole. So remember our molar mass kitty puts dirt over P. I'm going to rearrange to solve for density, which is molar mass times P over RT. Now I'm just going to fill in what I do know. And then after I fill in my knowns, I'm going to check that my units all cancel out. And that should give me the right answer. Moles, moles, atmospheres, atmospheres, K, K, and I'm left with units of grams per liter, which is what I'm looking for. Let's keep rolling on to number 5. We have a 2.00 liter flask filled with propane gas at a pressure of 1.00 atmospheres, a temperature of minus 15 degrees Celsius. Let's go ahead and turn that into Kelvin by adding 273. I get an answer of 258 K. If you get a negative answer for any of these problems, you would say, ooh, I made a mistake here. And in this case, that mistake would have been not changing Celsius to K. And we are solving for the mass of the propane in the container. The other thing is we are given the chemical formula, so I can actually calculate the molar mass of propane by adding up 3 carbons with 8 hydrogens to get 44.094 grams per mole. There's a couple ways that you can solve this to get the mass. Is once you have the molar mass and add it up, you can get grams by multiplying by the number of moles. So you can do PV equals nRT, solve for N, and then change grams to moles using the molar mass. Or you can say that density is equal to molar mass times P over RT. And we can go on further because density is actually equal to mass over volume. And we can move the volume away from the mass by multiplying. So mass is going to equal molar mass times P times V over RT. So now it's a matter of plugging in my numbers. 44.094 1 atmosphere, 2 liters, over R T. K's cancel, liters cancel, atmospheres cancel, moles cancel, and I'll be left with units of grams. Okay, let's solve for the density here. So density is equal to molar mass, P over RT. Chlorine gas, you have to be careful because chlorine is one of our diatomic elements. If you don't remember what that is, go back and watch the diatomic elements video. So it's not going to be 35.45 grams per mole as in Cl. It's going to be 70.90 for Cl2. And temperature, of course, has to be changed to Kelvin every single time for 295. K's cancel, atmospheres cancel, moles cancel, and you're left with units of grams per liter. Grams on the top and liters on the bottom is acceptable units for density. So what is the molar mass? If it has a density of 0.480, temperature of 260 degrees Celsius. I'm going to change that to Kelvin right away. And a pressure of 0.140 atm. This is just plugging it into the formula. Cancel, 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 and we get units of grams per mole, which is acceptable. This right here, if it looks like that, don't let that confuse you. That's 1.50 times 10 to the 2 grams per mole, which is, I'm going to move it over 1500 grams per mole. And it's written like this because in order to have this has two significant figures, but our answer needs to have 3. So we have to answer in scientific notation in order to have the correct number of significant figures. The lowest pressure achieved in a laboratory is about 1.0 times 10 to the minus 15 millimeters of mercury. Millimeters of mercury is actually taking a ruler and measuring the height of a column of mercury on a barometer. So millimeters is typical in measuring how high it goes. You can also see centimeters of mercury. So 1 atmosphere is equal to 760 millimeters of mercury, or 76 centimeters of mercury. So let's work on that conversion factor. Pressure is equal to 1.0 times 10 to the minus 15 millimeters of mercury. 760 millimeters of mercury in 1 atmosphere. How many molecules? This time we're looking for molecules. So we know the conversion factor in 1 mole, there is 6.022 times 10 to the 23rd molecules, always. A mole is a counting number. That is just like a dozen is always 12. 1 mole is always 6.022 times 10 to the 23rd. So we're looking for how many molecules. The volume is 1 liter. And the temperature is 22 degrees Celsius, which is 295 K. Okay, I'm going to calculate this out. It's going to be 1.316 times 10 to the minus 18 ATM. Now, there's also a couple ways you can do this. You can solve for the number of moles. And PV equals nRT becomes N equals PV over RT. Pressure, 1.316 times 10 to the minus 18 ATM. Volume, 1.00 liters. R, times T of 295. And this gives us an answer of 5.435 times 10 to the minus 20 moles. If that's how many moles you have, we'll multiply it by Avogadro's number in 1 mole. There's 6 times 10 to the 23rd molecules. And I get an answer to 2 significant figures of 33,000 molecules. So determine the density of CO. So the molar mass is carbon plus oxygen, or 28.01 grams per mole. Pressure, 785. We'll divide that by 760 because there's 760 millimeters of mercury in 1 atmosphere to get 1.0329 atmospheres. Not worrying about significant figures. And a temperature of 85 degrees Celsius. I'll change that to Kelvin right away to get 358 K. So density and then we're just plugging in 28.01 1.0329 for R. And T. Grams per liter is my units. All good. This one didn't give you the answer, so let's calculate that out. 28.01 times 1.0329 divided by the bottom. Gives me an answer of 0.9848 grams per liter. And we would need 2 sig figs, so 0.98 grams per liter. Move on to number 10. Molecular mass is the same as molar mass. Molecular weight, is the same as molar mass. They gave us the mass of 3.042 grams, volume of 426 milliliters. I'm going to change that to liters, move the decimal point over 3.426 liters. Temperature is 0 degrees Celsius, add 273, and the pressure is 1 atmosphere. So molar mass, Kitty puts dirt over P, and dirt, D, is actually density, which is mass over volume, RT over P. All right, units. I was careful to change all my units before I even got into this, so I'm all good. And I get an answer of 159.97 grams per mole. And let's answer in sig figs of 3. An unknown gas has a density of 3.167 grams per liter at STP, which is 273 K, and 1 ATM. So the molar mass is equal to 3.167 grams per liter. When you calculate that all out, you get 70.9 grams per liter. Now I have to compare them to the possibilities for the unknowns. So you're going to look on the periodic table of the elements, and you're going to find the gases and add up their molar masses and see which one makes sense. So this one is 39.95 grams per mole, so it can't be argon. Oxygen is 32 grams per mole because it's 2 O's. Chlorine is 70.90 grams per mole. HF is 20.008. And water is 18.016 grams per mole. Once I got to chlorine at 70.90, I know the identity of my gas is chlorine. So here we're looking for the molar mass. The other thing I can do with the density is calculate right off the bat its mass over volume. So it's 0.30 grams over 0.082 liters and get the density right away so I can plug it in if I want to. That's another strategy you can use. Remember, in chemistry class, there's always more than one way to solve a problem. So molar mass is equal to density ideal gas law constant temperature over the pressure. Okay, let's do this one really quickly. Density is what we're solving for. The molar mass I can add up by adding 1 oxygen to 2 fluorines, and that is 38 plus 16, or 54. The pressure is at STP, so 1 atmosphere, and the temperature is 273 K. So density is equal to molar mass times pressure over RT, or 54 times 1 over the ideal gas law constant times the temperature. Double check your units always. And we'll answer to, oh, look, they didn't give us sig figs. So I'm going to say that I use the periodic table of the elements, so 4. And my answer will be 2.410 grams per liter.